Hopefully. But, okay, now
You have to press the mouse and then it works sometimes.
Oh, okay, I see. Thank you. So this talk is going to cover a pretty broad range of topics, but I'm going to try to get through everything as best as I can. So first I'm just going to start with a very general question, where do neutrinos come from, which is still a very open question when it comes to astrophysical neutrinos. And closely related to that question is, what are the interactions involved in neutrino production, especially for neutrinos measured at high energy detectors such as IceCube, where we see astrophysical neutrinos. Oops. Then after that, from there, I'm going to talk about our understanding of deep-inelastic scattering, which is the relevant domain in IceCube and high energy experiments like IceCube. And then from there, moving on to describe inelasticity as a powerful tool for probing high energy neutrino properties, and looking for new physics with neutrinos, such as, for example, measuring the astrophysical neutrino-antineutrino ratio. And finally, if there's time, I'm going to talk about some nuclear effects that can be relevant in neutrino interactions at high energies. So starting with where neutrinos come from, neutrinos appear at a lot of different energy scales. So at the lowest scale, we have neutrinos coming from the early universe, taken together. That is going to consist of what we call the cosmic neutrino background, and it covers the range, a range of energies from 10 to the minus 6 eV to about 1 eV. Then from there we have neutrinos from nuclear reactors, the first neutrinos that we were able to measure, geophysical neutrinos, and solar neutrinos. And it was solar neutrinos that gave rise to the solar anomaly. So basically what happened with both solar and atmospheric neutrino measurements is that we were seeing less neutrinos of a given flavor than we expected. And then Super Kamiokande was able to robustly confirm that observation. And moreover, in the case of atmospheric neutrinos, it observed differences depending on the direction. So this said was that this depended on the distance that the neutrino traveled. And so this phenomenon was later described as neutrino flavor oscillations can be explained by neutrinos having a mass. At these intermediate energy ranges, we can have neutrinos from supernovas, so these can either be transient fluxes from individual supernova or an aggregate flux coming from the extragalactic scale. And then up until 100 TeV, we predominantly see neutrinos from the atmosphere. And so like I mentioned, so these primarily come from cosmic ray interactions with the atmosphere. And we can divide them into a prompt component where we have neutrinos coming from charged mesons, and these result in more or less equal amounts of electron and muon neutrinos. And then we can have conventional neutrinos, which are neutrinos coming from charged and neutral pions and kaons produced from cosmic rays. And so in conventional neutrinos, we get more muon neutrinos as opposed to electron neutrino flavors. And as I mentioned before, atmospheric neutrinos also play a role in discovering neutrino masses. So in the neutrino standard model, the probability for an electron neutrino to convert into a muon neutrino is given here. And it comes with a characteristic oscillation length, which is the length required, the minimum length required in order to measure a neutrino oscillate between two flavors. And so it's proportional to energy, which means that mass-induced oscillations dominate at lower energies. And the space on the right is a useful way to visualize this, where these dashed lines are constant L/E lines. And in particular, with these distance and energy scales, this part right here, this portion right here is completely opaque to gamma rays because of absorption with background radiation. So neutrinos, apart from gravitons, neutrinos are really our only window into looking into that region. So let's say, for example, for hypothetically, let's say we wanted to measure delta m squared of 10 to the minus 21. It's unrealistic, but we would want to lie on this L over E line right here. And if we measure the probability of a muon neutrino staying as a muon neutrino, then we would see a dip over here where it changes flavor. And at L over E much smaller than this particular value, the probability of muon neutrino converting to electron neutrino goes to 0. But for L over E much smaller, the oscillations are too fast to probe. So we want to build our experiment with the right parameters so that we can be able to detect this oscillation. And for example, if our experiment was to be sensitive to this energy right here, we would need the neutrino to travel at least 10 kiloparsec in order to be sensitive to that. But thankfully, the actual delta m squared is much larger than 10 to the minus 21. So we can already be sensitive at the scale of atmospheric neutrinos and solar neutrinos. And the way that we measure oscillations with atmospheric neutrinos in particular is by looking at different directions, since the neutrinos travel different distances, and so they arrive at the detector with different flavor configurations. But beyond 100 GeV, the neutrino oscillation length exceeds the diameter of the Earth. And as neutrino energy increases, the absorption through matter becomes more and more important. And so at 40 TeV, the neutrino absorption length is about equal to the Earth's diameter. So there we see effects of Earth absorption. At higher energies, we have neutrinos coming from astrophysical sources. So these can also be cosmogenic neutrinos coming from cosmic rays, high energy cosmic rays. We can have the Milky Way, we can have blazars, all sorts of different things. And when it comes to the unknowns, what we really don't know about is these two extremes, the very low energy and the high energy range right here. And IceCube in particular is an experiment that has measured neutrinos at this very high energy extreme. Where these neutrinos come from is still unknown. It can come from a combination of all of these different kinds of sources, but generally we assume that the diffuse flux can be parametrized as a power law, where we get a lot of neutrinos at lower energies, and it starts to taper off at higher energies, which is typically at about a few hundred PeV or so. IceCube has seen neutrinos from confirmed individual sources. So for example, from the flaring blazar TXS, also from the active galactic nuclei NGC 1060, active galaxy, sorry. And also recently it observed neutrinos from the galactic center, confirming that as a source of neutrinos as well.
I'm a little bit lost with the energy scale. So if I think about a supernova explosion, which is very violent, but it's MEV physics, right? I mean, this is not 10 to the whatever 12 something electron volts. So where do the neutrinos get this energy from, really? I mean, I mean, everything what happens is nuclear physics which blows this up. So I can't see the energy scale where I get a 10 to 12. How does it get accelerated to this speed?
I mean, usually, so I'm going to get to production mechanisms.
Okay,
because those are not known either, but I mean, it can be, depending on the source.
That's exactly my question.
Well, I think if the source is boosted, a relativistic boost,
but then
you can get arbitrarily large.
Yeah, that much I understand. I can do this always with the Lorentz transformation,
Absolutely.
right? So but then I need tremendous boosts, right?
That's a supernova explosion.
It comes from the remnant of the supernova afterwards. You're left with strong magnetic fields, which can act like a particle accelerator. You know, you have kind of 1,000 years before the magnetic fields deteriorate.
Okay.
So that you have to boost the hadronic product, which will eventually produce a neutrino, so that they get accelerated in the field.
Yeah.
But that's a mega accelerator, right? I mean,
Well,
I mean, the typical is at best a GeV for a neutrino, right? I mean, from a hadronic, from a QCD process, right?
Well, no, but the
so
source
we have cosmic rays going up to 10 to the 20th eV.
Yeah, well, that's
And
fine.
if they hit a beam gas, hit a beam gas interaction, you can get neutrinos 5 or 10% of that.
Right.
I mean, we don't think supernovas can go to 10 to the 20th EV, but there's something out there that can.
Yeah, okay. That's my question. What is it? Okay, you say it's an
Yeah.
accelerator in the magnetic field. Okay, fine.
Yeah, that can either be in the form of an active galactic nucleus or some other thing.
So I was gonna ask a question on the previous slide, which it looks like you're about to answer, but I'll ask it anyway. Cosmic rays get all scrambled in the magnetic field and kind of fields all over the place.
Yeah, that's why.
So if you do find something that's pointing,
Mhm.
there's only a limited number of ways to produce that, right? I mean, not generic. I mean, if it just emits cosmic rays, they travel forever and then decay.
Yeah.
You're not going to be able to associate it with the source.
Yeah, but in the case of neutrinos, they don't get scrambled.
Sure, but they have to be produced. I guess. Sorry, say another way. They have to be produced. The neutrinos themselves have to be produced relatively close to the source.
Right. Yeah, because then they don't bounce scatter. They remain at high energies. Yeah, but generally, yeah. So like you see over here, we can get neutrinos are typically coincidentally produced with photons. So we have gamma ray detectors trying to detect sources coincidentally with neutrino detectors as well. But generally speaking, the source is largely remains unknown. But a very useful question that might answer, at least partially help us answer some of these questions, is what the astrophysical nubar ratio is. So it's a bearing on a number of things, such as like what the astrophysical energy spectrum looks like, what production mechanisms are involved at the source, and also what type of source it is, what the various properties of the sources like photon density, magnetic field strength, cosmic ray mass composition, etc. For example, I mean, there are a lot of different mechanisms that can get involved. Generally speaking, we can have PP production, which is largely expected to happen in star-forming galaxies, and then P gamma production, which can happen in active galactic nuclei. And in the case of PP production, we might end up with equal amounts of neutrinos and antineutrinos in both electron and muon flavors. But if we have a muon down source, we only end up with muon neutrinos and no electron neutrinos. In the case of P gamma interactions, we can end up with equal amounts of muon neutrinos and antineutrinos, but no electron antineutrinos. And then if that is also muon damped, we would only end up with muon neutrinos. So each of these has a different nubar ratio associated with it that's also flavor dependent and could point us to what types of production mechanisms and sources are involved in producing astrophysical neutrinos. But up until now, the only measurement to date has been the detection of glass shower resonance, which detected an electron antineutrino.
What is a glass shower resonance for the non-expert?
So it's when a neutrino interacts with an electron at high enough energy to resonantly produce a W boson.
A W boson?
W,
Okay.
yeah. Yeah, so IceCube detected one event. The drawback of this is that it's only one event. It only gives us access to the electron component. It's restricted to PV energies. So the question is there a probe that can discriminate neutrinos from antineutrinos at lower energies and across other flavors? So from there, this is where we can ask if the interaction process at the detector can help illuminate what happens at the source. And so according to the standard model, neutrinos interact in one of two ways. You can either have a neutral current interaction with a boson exchange on the left, or a charge current interaction with a W boson exchange on the right. And in the case of a neutral current interaction, all that we have to work with when reconstructing the initial neutrino energy is the hadronic cascade that results. But in the case of a charged current interaction, we have to use a combination of the outgoing hadronic cascade and then the radiation from the lepton to infer the neutrino energy. With the hadronic cascade, the nice thing is that it tends to be pretty contained. So it has relatively good energy reconstruction. But in the case of charge current interactions, again, it has to be, the neutrino energy has to be inferred from the combination of the two outgoing showers and some, which leaves a lot of room for error in the form of missed energy. But in the case of charge current interactions, we could introduce a variable called inelasticity, which is a measure of the fraction of the initial neutrino energy that gets converted into the outgoing hadronic shower. So apart from inelasticity, we can also use two other variables. There's a form momentum transfer and Bjorken X. And using these variables, we can write the differential cross-section. Below 100 GeV, interactions with valence quarks dominate, where the different couplings between W and U and D quarks leads to different cross-sections for neutrinos and antineutrinos. But then at higher energies, we have C quarks dominating, and that erases the difference between neutrinos and antineutrinos. And in particular, above 50 GeV, neutrino interactions are dominated by deep inelastic scattering. So this is described by a large momentum transfer that breaks up the nucleon target into its constituent parts. And so typically, in the case of deep inelastic scattering, the invariant mass of the final state hadron is greater than 2 GeV, or greater than the mass of the target nucleon. And in simple terms to first order, we can write the double differential cross-section in terms of 3 structure functions. And then a neat repackaging of it is the one on the second line, where typically at first order, according to the quark parton model, the longitudinal structure function is 0. So this simplifies things quite a bit. And each of the structure functions at first order can be written in terms of a combination of the active quark parton distribution functions. So for example, for neutrino scattering off of the neutron, this is how we would write the structure functions. And then on the bottom, if we want an antineutrino scattering off of a proton, we just interchange U and D. And so on the right, I show the quark PDFs for when we set Q squared to 100 GeV squared. So you can see at high X that the valence quarks dominate, but then when we go to low X, we get C quarks. The C quarks become more important. And these quark parton distribution functions denote the probability that a given quark carries a fraction X of the hadron's momentum. So plugging all of this in, we can simplify our neutrino and antineutrino cross-sections as follows. And so we can see that the difference here, I forgot to mention that in this expression, the plus corresponds to neutrino cross-section, minus corresponds to antineutrino. The differences between the two are proportional to 1 minus y squared. Beyond leading order, the structure functions are related to quark PDFs through convolutions with expansions of the coefficient up to some order of alpha s. So they're a little bit more complicated. So if we integrate over Bjorken X, we can plot the inelasticity distribution normalized to the total cross-section. And over here, I plot the neutrino and antineutrino PDFs as a function of inelasticity. So you can see there's quite a, this is for 1 TeV, there's quite a bit of big difference between neutrinos and antineutrinos and how they depend on inelasticity. So for neutrinos, for example, the inelasticity distribution is much flatter, and then for antineutrinos, there's a preference for smaller inelasticity. And this difference between neutrinos and antineutrinos and inelasticity is most prominent at lower energies. So you can see over here that at the lower energy end of about 100 GeV, to a TeV or so, we get the largest difference in neutrinos and antineutrino inelasticity, but then as we go to higher energies, C quarks dominate and this difference converges. Yeah, and so there's also a difference in the total cross-section between neutrinos and antineutrinos. Although the behavior, the trend is mostly the same for both of them. So in each case, deep inelastic scattering, as you can see on these plots, compared to other forms of neutrino interactions, starts to dominate around 50 GeV or so. And then from there, it grows approximately linearly as a function of energy. And the suppression in the case of the antineutrinos is because of that 1 minus y squared term that we saw before. Now, in the lower energy and a lot of the data that we have for neutrino charge current cross sections comes from accelerator data like BEBC and CHARM. So these are shown over here. Recently, this has also been extended to slightly higher energies by Fraser-New, and so the result is shown in red over here. And then IceCube has also been able to supplement these measurements. So on the left, we have a measurement of the multi-TeV cross-section using Earth absorption as a way to infer the neutrino cross-section in matter. And the error bars, so the result was about 1.3 times the prediction, the standard model prediction, but the error bars are pretty large, so it covers that. And on the right, we have another slightly higher energy analysis that measured the cross-section. Both of them are consistent with standard model predictions up to 1 sigma.
So these green points are data, and these blue points on the left?
No. So these are predictions from standard model
And what is the data? The shaded thing or what? Or?
Yeah, the data, yes. This is the interpolated data.
Okay.
Yeah, with the 1 sigma band. And then this, yeah, so sorry, this is the same thing as the one on the left.
Okay.
Yeah.
So the red curve is the theoretical prediction given what we know about the neutrino-antineutrino ratios. You compare that with the blue curve.
Great. And then the green and blue are neutrino and antineutrino separately. So to put everything together, we can visualize things in this kinematic space of q squared and x. And neutrino DIS is typically considered to be above this blue range right here. So above the space where the invariant mass squared of the final state is greater than the target nucleon mass squared, which is the inelastic part of deep inelastic, and also when q squared is much greater than the target mass squared, which is that deep part. So the current data points that I showed before, this is just a sample of them, mostly come from accelerator data like BEBC, CHARM, UTEV, and from the LHC. But recent measurements from IceCube of the mean inelasticity target lower energies where we expect the difference between neutrinos and antineutrinos to be the largest. And so just as a caveat, these are mean inelasticities, so these would map onto, these would be, the true inelasticity would be a distribution, and so this would be a range. But for given energy and measured inelasticity, we can map onto a line in the q squared x phase. So these 3 data points are from that IceCube analysis, and also an older IceCube measurement of inelasticity of neutrino DIS covers slightly higher energies. And IceCube has produced cross-section measurements in this region, and ongoing measurements using more data are currently underway. So just a little bit about the IceCube detector. It's a kilometer cube detector located in the South Pole in the ice cap. It consists of an array of strings consisting of digital optical modules located between 1450 and 2450 meters below the surface of the ice. And it also consists of a denser array called deep core, which is meant to measure slightly lower neutrinos at slightly lower energies, typically used for oscillation measurements. And so if we zoom into these digital optical modules, they would look like this. So the bottom half consists of a photomultiplier, and then the top half consists of equipment that converts the charge collected from the photomultiplier into a signal, and then triggers it up to the IceCube lab at the surface. And so what IceCube measures is Cherenkov radiation from charged particles going through the ice. And so as these charged particles travel through the ice, so for example, in the case of the muon, it ionizes the atoms in the ice. And if the muon is traveling faster than the speed of light in ice or in the medium, the light that gets emitted interferes constructively. And so then we end up with a cone of radiation, which is called Cherenkov radiation. And so this is an example of an event display in this case, a muon, a charged muon going through the ice. And the red color is earlier times, green color is later times. And so here we see the bulbs representing the amount of charge that gets deposited into the DOMs. And the way that we classify these events, or a way that we can tell what types of neutrino is involved, is through different event morphologies. So, for example, we can get cascades. These are typically all flavor neutral current interactions or charged current nu E interactions. We could also get tracks, which happens when we get an outgoing charged lepton. And these are typically what we get. These are signatures of charged current nu mu interactions. And we can also get double bangs, which is when a new tau interacts in the ice and produces a tau lepton. That tau lepton quickly decays and then produces a shower. And so in the case of cascades, we have pretty good energy resolution, but not so good angular resolution. But then for tracks, we have pretty good angular resolution, but not as, the energy resolution is not as good. In the case of tracks, we can subdivide them into two different types. So, for example, we can have starting tracks, in which case the interaction vertex lies within the detector. And because of that, we get improved energy reconstruction because more of our deposited charge is contained within the detector. It also allows us to reconstruct the inelasticity better. On the other hand, through-going tracks, when we have an interaction vertex outside of the detector, tend to consist of slightly higher energy events. And they also have poorer energy resolution because of the missing information. They're typically used in analyses measuring oscillations or interactions through the Earth. Something else that we do in IceCube is apply cuts to events in order to eliminate as much background as possible. So the largest background in IceCube comes from atmospheric muons, which can mimic a charge current interaction produced by a neutrino, converting into a muon. So a nice way of eliminating that background is only choosing events from above the horizon, below the horizon, and where the direction is parametrized with what's called a zenith angle. So we would, in this case, we would choose events below 90 degrees, or above 90 degrees in this parameterization. And that, from here, we can see eliminates a lot of the atmospheric muon background that we would otherwise detect. And so we're left with mostly just atmospheric neutrinos, but there are other event cuts, as we'll see soon, that we can apply as well to get rid of background.
So can you go back, if you have a muon, like your right muon on the right side,
yeah.
If I understand it right, this muon comes in and then makes a neutrino somewhere in the middle of the Earth, and then the neutrino flies down. Is that what it is?
No, the muon gets absorbed. Yeah, it doesn't produce a neutrino. So in that case, if it were to produce a neutrino, it would this would not work as a way to eliminate the background, because this is background.
Exactly. So what do you do about those? When the muon convert makes me a neutrino and the neutrino goes into a detector, how can you distinguish this from a cosmic mirror atmospheric neutrino which comes in? I said you don't care about the difference.
I mean, the likelihood of creating a neutrino.
Muons lose energy before they decay typically.
Mhm.
That is an issue with taus. You know, you can have a tau neutrino comes in, interacts in the Earth,
Yes.
you produce a tau which travels, hundreds of meters or kilometers, decays, produces a new tau of lower energy, and we call that tau regeneration.
Mhm.
But for muons, it's not an issue.
Yeah. So I mentioned this before, but an older analysis in IceCube measured the inelasticity using a combination of cascades and starting tracks between 10 to the 2.5 GeV and 10 to the 7 GeV. And it was one of the first neutrino analyses to use inelasticity as a new variable. And it also used it to make inferences about the astrophysical flavor composition in the sample, neutrino charm production above 100 TeV, and atmospheric neutrino antineutrino ratio. Specifically in the case of charm production, the branching ratio of charm production from charge current neutrino interactions increases from 10% at 100 GeV to 20% at 100 TeV. And because of the distribution, because of the PDFs of C quarks, and usually in the case of charm production from neutrinos, the predominant mechanism is through interactions with strange quarks. We get a flatter inelasticity distribution compared to when they interact with valence quarks. And this becomes most visible as a signature above 100 TeV and at high inelasticity. Additionally to that, there's a 10% chance of the charm quark decaying semi-leptonically, in which case we get two showers that get reconstructed as a single muon, and that leads to a lower apparent inelasticity, which can also be a signature of charm quark production. And so we can see, for example, this is the PDF that I showed earlier. But in the case of strange quarks, we get a flatter distribution at high X compared to valence quarks, which is what leads to the different distinctive inelasticity distribution. So once we have the inelasticity measurement, we can make inferences about the atmospheric nubar ratio as well. So on the right are the results from the analysis. And so as I mentioned before, the nubar ratio, we're most sensitive to it at lower energies. At higher energies, not only does nu and nubar converge, but in this case, our statistic also gets pretty bad, which leads to the higher error bars. But on this plot right here, we have the nubar fraction as a function of energy and inelasticity. And so we see that since nubar prefers lower inelasticity, we have more nubar at lower inelasticity compared to higher. So this is a more recent inelasticity measurement from IceCube, which targets lower energies and overlaps with accelerator data. And so this goes between 80 GeV and 560 GeV, and uses 10 years of atmospheric neutrinos using the deep core array, which is the denser array that measures neutrinos at lower energies. So this is sensitive to region below accelerator data, and it allows for us to compare to perturbative QCD calculations. It's also more sensitive to the atmospheric nubar ratio because of the difference in inelasticity distributions. And so on the left, we have using that inelasticity measurement to predict the measured neutrino fraction in the atmospheric flux using different cross-section models. And in all of these cases, the agreement is within 1 sigma. And on the right, we have a comparison to different models of the cross-section and also the atmospheric flux. And in all of these cases, the agreement is within 1 sigma, except the error bars are fairly large. And so there's hope that more data, we can improve these results eventually. But thus far, astrophysical neutrinos have helped us. We've seen how they've helped us access higher energies to learn about neutrino DIS cross-section and elasticity. The question is, can we turn this around and use neutrino deep inelastic scattering and what we've learned about neutrino interactions to learn more about astrophysical neutrinos themselves. And so for this, remember that inelasticity is a variable that allows us to discriminate between neutrinos and antineutrinos, but this is mostly true at lower energies where we have less astrophysical statistics. On the other hand, we can use starting tracks to help remove atmospheric muon background while also reconstructing inelasticity. So is there a way we can combine these in order to get sensitivity to astrophysical nubar? And for that, there is a sample with an IceCube that uses high energy starting tracks. This is a sample that has been used in the past in order to get a fit of the astrophysical neutrino spectrum as shown on the right. And so the sample in particular is shown in green. Not only is it good because it uses starting tracks which have good energy, comparatively good energy resolution, and tracks in general have good angular resolution. It also includes a dynamic self-veto in the southern sky, which eliminates most of the atmospheric muon background by eliminating events where we have interactions occurring in the veto region. And so we could see the astrophysical purity that results because of applying the self-veto. In this case, with these distributions where the astrophysical events are shown in purple, the atmospheric are shown in blue. So at the energies at which we expect to have sensitivity to nu and nubar, to the nu nubar ratio, we have pretty good astrophysical purity. And so this right here is an example of the self-veto effect in the southern sky. These are the resulting inelasticity distributions. So if we vary, for example, the event distributions in inelasticity, if we vary the astrophysical nu-nubar ratio on the left, we get these different distributions in inelasticity in the event, predicted number of events. And on the right is the total distribution combining astrophysical and atmospheric events when we vary not the astrophysical nu-nubar ratio, but the atmospheric nu-nubar ratio. And the way that we vary them is by applying weights based off of the dp/dy distributions that I showed earlier. And so you could see there's a pretty large difference in the number of events that we expect when we vary this parameter. So currently, this is the projected sensitivity in the space of, on the x-axis, the atmospheric nu-nubar ratio. So specific, this is not technically the nu-nubar ratio, but it's the varying the nu-nubar ratio predicted from atmospheric flux predictions. So scaling that between 0.8 and 1.2 so that we can retain the energy dependence and zenith dependence of the nu-nubar ratio as opposed to applying a blanket nu-nubar over all energy and zenith. And then on the y-axis, the astrophysical nu-nubar ratio. So here I show the 1 sigma and 2 sigma sensitivity. And here is the statistics only plus statistics and systematics just to get a sense of the effect of the detector and physics systematics in our results. And currently this is under unblinding. So I expect to have a result soon and I expect to be presenting that at this year's IceCube conference. But having presented the projections, what more can we learn about neutrino-nucleon interactions that can further add to this picture? So we can have, so far we've considered the simplest model of neutrino interactions. So this is first order functions, structure functions along with an isoscalar target. But there are a number of other things that we can consider. So for example, first, how do higher order radiative corrections impact neutrino inelasticity distributions? So one of these corrections can come in the form of final state radiation, where we get the the outgoing lepton radiates a final state photon. And in this case, we use the calculation in this paper right here that modifies the double differential cross-section. Where we introduce the parameter z. So the variable z denotes the fraction of the lepton's energy that remains after it radiates a prompt photon. And the energy that gets radiated away by the photon gets combined with the hadronic shower in the reconstructed cascade. So this leads to a larger apparent inelasticity than we would have had there not been a prompt photon. So with final state radiation, you can see here, in the case of a neutrino energy of 100 GeV on the plot on the left, the differences with and without final state radiation. So with final state radiation, we have a preference for higher inelasticities. This is a slight preference, but this difference grows as we increase in energy, both for neutrinos and antineutrinos. And just as a note, I included this in my new nubar analysis, this effect. Another question we can ask is how does the structure function dependence on nucleon targets affect neutrino cross sections and uncertainties? So, for example, we can calculate the cross section off of a proton or off of oxygen, and we get different quark per ton distribution functions. So, in the case of the proton, the valence quarks are more prominent at higher x as opposed to oxygen. And so starting from this deep inelastic scattering cross-section, we calculate the structure functions for different targets. And then in order to arrive at, for example, a hydrogen, a cross-section with a hydrogen target, we plug in the parton distribution functions for proton and oxygen, and then we weight them according to the mass numbers. And so this is a comparison of the inelasticity distributions on an isoscalar target compared to water. And so in both of these cases, we can see that if we calculate these using water, there is a preference for slightly higher inelasticity. So there is a slight difference in the resulting distributions that we get. But not only that, we also have the effect of nuclear shadowing that we have to take into account. So for example, nuclear shadowing, we can model it using a nuclear modification ratio, which is a ratio that compares the structure functions for corresponding to a nuclear target compared to a free proton or free neutron. And so we get various different, we get this kind of behavior as a function of x, where we get shadowing at low x, anti-shadowing maximum, and then we get an EMC minimum. And so what this looks like for 3 different targets shown here for U bar is we get this kind of behavior for these different targets showing these effects. And these are this is what it looks like in the case of neutrino scattering for different targets as a function of inelasticity, as opposed to Gurkenx. So in the case of a proton in the top panel, D quarks dominate in neutrino cross sections, while U quarks dominate in anti-neutrino cross sections. At large Y, X grows smaller with increasing neutrino energy, and so C quarks begin to dominate, causing R to approach unity. At small y, valence quarks dominate, with the largest difference appearing at y below 0.1, which agrees with what we see here. For water, the rise at low y corresponds to the high x anti-shadowing, while the minimum in R corresponds to the EMC region. And as the neutrino energy grows, anti-shadowing in EMC regions get compressed at low y. At high y, the behavior corresponds to shadowing, and the rises in high y is slightly larger for antineutrinos because of increased in shadowing in that case. And so this leads to the question of what is the effect of nuclear shadowing and when do we have to start paying attention to uncertainties. This is an issue because there are differences between predictions from different data sets. So for example, just starting off with EPPS 16 and EPPS 21, which adds data from proton-lead collisions at the LHC and Jefferson Lab deep-inelastic scattering measurements at low x and low p squared. We get these differences in the resulting R distributions as a function of x for lead. And so you can see there's much, there's a pretty big difference in the predicted distribution. And also, not only that, but there's differences between EPPS 16 and NNN-PDF, which includes Atlas WNZ 2011 data, as well as strange quark-sensitive new TeV cross-section measurements. So over here we have a prediction for the ratio on iron in the case of a U quark. And so the uncertainties in this case from NNN-PDF are larger than those from the previous EPPS dataset. But in the case of strange quarks, there's an overall 20% suppression in the nuclear modification. And there are smaller uncertainties in NNN-PDF, probably mostly due to the fact that it includes the strange sensitive new type cross-sections. However, there are larger uncertainties in valence quark modifications. So as we saw earlier, there's also this divergence at high x, where we get a tampering, but previously with EPPS, it shoots up. And so the question of which uncertainties to include or exclude in neutrino analyses remains, depending on which regions the analysis is probing. And finally, there's also the question of when do heavy quarks become important. And so up until now, we've only been including leading order contributions. So for example, in the case of a charm quark, the F2 structure function can be written in terms of the CKM coefficients and the parton distribution functions. And many previous PDF calculations relied on the zero mass variable flavor number scheme where heavy quarks decouple below the quark mass threshold. And then they're treated as massless partons otherwise. So we neglect terms of order m squared over q squared or higher. But in order to include a heavy quark treatment, we can use the general mass flavor varying number scheme, which combines the previous scheme with a decoupling scheme at the quark threshold. So the first term in blue is computed in the massive heavy quark scheme. Then we have a damping term. So once we go past the mass quark threshold, the purple term is computed in the massless scheme, and then the orange term is computed in the massless limit as the mass of the heavy quark goes to 0, and it's subtracted from that in order to prevent double counting. And so for all of this, we use the Apple software to compute the structure functions at higher order in different schemes. And so this is the result for F2, comparing the two different schemes with one another. So pretty large uncertainties. And the way that we calculate the uncertainties is by summing over the eigenvectors for each of them, eigenvector PDF members, and their variations from the central PDF. And these are provided at the 90% confidence level in this case. And then for molecular targets, we propagate these by summing over the individual nucleon contributions and dividing by the sum of the mass number. So in this case, in the case of F2, the uncertainty is large at low x, but then it converges to 1. But then the ratio converges to 1 at high x. But then for FL, it's slightly different. There's a pretty large divergence. And then this is F3. So on the left, we have the zero mass varying flavor number scheme. And on the right, we have the heavy quark treatment. And so at small x, we do have a pretty big difference between the two for neutrinos and antineutrinos. But then these also converge at higher x, which would correspond to lower inelasticity. And then this is the predicted cross-section when we use the heavy quark treatment compared to assuming a zero mass scheme. This is from NUTEP. So this is just as a reference, but this is also something that was included in my analysis, and it's something that we pay attention to as we go to lower X and higher energies. So as a summary, measuring inelasticity and neutrino deep-inelastic scattering can act as a powerful probe of nucleon structure and see quark content through the weak interaction. And while mass oscillation measurements can reveal properties that neutrinos exhibit during propagation below 100 GeV, inelasticity can tell us a lot about the production and detection, so the two endpoints at higher energies, and can also give us answers to important outstanding questions in neutrino astrophysics through its sensitivity to the flavor ratio and the nubar ratio. And so the first measurement of astrophysical nubar is set to be presented at this year's IceCube from IceCube, considering the unblinding goes well. That's all that I have for today. Thank you.
Good number of questions during that talk, but are there more?
So how much do you need to know about PDFs if you want to go really up to your multi-TV? Are they known, these PDFs? I mean, the LHC can only go so far, right? And so
Yeah, that's the question. I mean, there's been a lot of talk about this in IceCube, well, in inelasticity. Specifically, like how do we account for these differences in uncertainties? Because like, depending on which PDFs we choose, we get different. How do we model our uncertainties properly when we calculate the cross sections and predictions? So this is kind of a source of, especially at high energies. I think this is a source of contention.
that goes on in the systematic error.
Yeah.
So actually, one question, if we don't mind turning the tables. So, EPPS 16 had very little shadow at Q squared of MW and C squared, which was also matched by by intuition. But some of these newer ones, particularly EPPS 21, still have significant shadowing at the ZMAS, and a lot of that comes from Atlas and CMS data on W and Z production and PA collisions. So, and you wonder, could there be some other things going on in that data? And so what's your intuition about shadowing at large?
I have no idea, but I can recommend to go to our hit on Thursday, where Michael Klein actually he seems to be working on this forever, right?
Okay.
So he might give you a better answer than I cannot.
They don't specify Q squared, these are always at the ZMAS? Is that how I plot it?
Oh, the Q squared here is 100.
Okay.
Yeah, sorry about that.
So how do you know your Q squared actually? Do you measure this? I mean,
So this is from the NNN PDF.
That's from the extracted PDF.
Yeah.
no, but you make a measurement, and what Q squared? How do you know what Q squared reaction you have when you do it? Are you measuring the track so electron good enough that you can extract the momentum transfer? No, what do you? Whatever, is it a stupid
For these
question?
PDFs, it's outside.
We basically integrate, it's whatever the standard model gives you some, if you know the neutrino energy, you get some idea of the inelasticity, you can integrate over the Q squared with the probability that you get from theory.
Really, I mean, maybe I'm stupid, I'm probably stupid. So you see an outgoing electron and outgoing X stuff, all the other stuff. Then from that can I calculate Q squared? No, I can't either, right? I mean, I would know the ingoing and the outgoing neutrino, and then I would know the Q squared.
You could, in principle, if you could measure those directions well
Yes.
enough.
What's the matter? It's
Long
quantitative,
way from
right?
that.
You can constrain it, it's a quantitative question.
Right.
Okay.
So I integrate over a range, and how do I put the weighting on this?
So what you have is a muon track,
Yes.
that you can measure the direction quite well.
Okay.
And then the cascade where you cannot measure the direction very well.
Yes.
And in fact, in the region of overlap, you can't even do that great a job of separating the cascade light from the cascade and light from the muon. So, Gary was a plot in Gary's thesis about the angular difference between them. But that is mostly a plot about the angular resolution of IceCube and nothing to do about Q squared.
Let's use, okay, anyway, no, I'm still confused. Don't you need to know something about this?
No, you know from the standard model gives you some, if you know the neutrino energy and the inelasticity, you get some distribution of Q squares.
Okay.
Yeah, and then in our case, when we're plotting the inelasticity distributions, we integrate.
So maybe I missed it, but I didn't hear you say much about JLab and constraints on PDFs. Is that too low Q squared or not useful or what?
No, it's actually included in this data set right here in EPPS 21. So these are, I guess, outside of my area of expertise, but these are contributing in part to these differences in the.
Mostly at the very high X.
Yeah.
So for the shadowing and below, of course, there's also the focal.
Yep.
So there's a very forward detector in the LHC that some of us continue to be interested in, even though the U.S. Department of Energy is not. It will be built, in part by Norwegians and others, and the data will be there, and one can measure. I don't know how the cross sections go. I guess you want so this be extremely low X, but you want sizable Q squared, right?
Well, yeah. Everything helps. But.
Right. So, but the cross sections are sizable, so you can get reasonably large Q squared. We'll measure 4 very forward W's, very forward photons. So in the kind of the low X high Q squared region, there's probably more data coming.
That would be useful to include. Yeah.
If the neutrino is its own antiparticle, could these experiments give any measure of that? Since I think I've seen your graphs, you have different effects of neutrino and antineutrino based off your Y parameter.
Mm-hmm. So the neutrinos at Majorana.
Yeah, would that be in the realm of IceCube science?
There are other analyses that target Majorana, but they don't use they don't use inelasticity. I guess inelasticity would be hard to understand how. I have to think about that some more.
Okay.
Sorry.
Can you give me in just basic terms? I don't really know what shattering or AMC are.
Yeah. Oops. Where did I have that plot? So shadowing happens when we so this is a comparison between scattering off of a nucleus versus a free proton or free neutron. So when we take into account nuclear effects, we get this suppression of the cross section at low X, and then the EMC is based off of a measurement from the LHC, if I'm not mistaken. Right?
SPS.
Right.
European muon collaboration.
Exactly. That's
Okay.
30 years ago, 40 years ago, right? I think 85-ish, 80-ish.
Mm-hmm.
Yes.
But is there an understanding of why this happens, or is that just based on the measurement?
Yeah, there are many understandings as far as I understand.
It's over understood.
I'm not too familiar with
The best is the anti-shadowing. I can understand what a shadow is, but an anti-shadow must be a very bright light or something. That's why it goes up above one. I like the concept of the anti-shadow.
All right.
Any other questions? Okay, it looks like Basia again.